the University of Paris, Professor Alain Secudo showed me something extraordinary that happens when a really cold superconductor meets an ordinary magnet.
And there is levitation, you know?
And this little puck is just the tip of the iceberg.
Oh, come on. Let's go.
Back to the future!
I'm actually surfing above the ground.
I'm flying!
And it's more than just fun and games. Engineers in Japan are already scaling it up to create the world's first superconductor maglev passenger train. It flies above its tracks at speeds up to 311 miles per hour. And it's cold that makes it happen. So, what's the trick? You might think that the superconductor is acting just like a magnet.
This is now a magnet?
But you'd be wrong.
It's not like a magnet, because here you have both repulsion and attraction.
So these two disks have repulsion and attraction?
Both.
And that's not how a proper magnet behaves.
The attraction.
It can't do both at the same time. The superconductor can, because it warps the magnetic field of the magnet to a point where it attracts and repels at the same time.
It's both directions. It's
Yes,
a watch.
But how is this possible? How do superconductors actually work?
Look at that.
The crazy part is, scientists don't really know. It has something to do with that Q word.
Between the wheels and the track. The solution is to take both these factors out of the equation. It sounds like science fiction, but trains that do just that really exist. And they're called maglev, which stands for
magnetically levitating trains. There are no overhead power cables because the power source is built into the track. There's no friction from the wheels because, well, there aren't any wheels. The train is designed to float 10 millimeters above the track, so the only resistance it has is air resistance, which makes this train fast. Very fast.
Here at the transrapid test track in northern Germany, they're testing a technology that they hope has the potential to take over where the TGV meets its limits, with enough speed, not just for intercity, but for intercontinental travel. But like so many record-breaking trains of the past, not one, but two rival operations have been battling it out to turn this technology into the world's fastest passenger service. The German transrapid system and the Japanese JR maglev.
Maglev trains are all about magnets, and magnets have two poles, north and south. And when the facing poles of each magnet are the same, like in this instance north, north, they repel. Like so. The Japanese JR maglev system uses this force to lift their trains.
Magnets on the train face magnets with similar poles on the track, and the train rests on the repulsive force as if it's sitting on an invisible cushion.
Like so.
Japanese maglev trains have reached speeds in excess of 580 kilometers an hour using this system. But the technology is still confined to the test track. They've never managed to turn it into a commercially viable passenger train. While the Japanese system uses the repulsive force of magnets, the German system makes use of attraction.
But it's no use having the train sticking to the tracks. The trick to hovering is to use electromagnets. Now, an electromagnet is just a piece of metal with wire coiled round it, like so. And when you put some current through that wire, like this, it's attracted like so. When you switch that current off, it drops. Attract, drop, and so on.
And if you were to switch your electromagnet on and off fast enough, like this device does automatically, you can defeat gravity, attracting and dropping so quickly that metal objects like my toy train here appear to hover.
Incredible. I don't know about you, but I think that's pretty damn amazing. And that's magic. The Transrapid has massive electromagnets in here that sit under the track. And when the power is switched on, power on, bitte. The magnets are attracted to the track And now the train, the whole train is floating in midair 10 millimeters above the track with magnets at the side here to keep it steady.
A completely separate system of magnets built into the test track create a moving magnetic field that pushes the train along with it, just like a surfer riding an invisible magnetic wave. And this makes the system very efficient, because you only need to switch on the bit of track that the train is running over.
Now that click means that this section of track has just been electrified or energized, and that means the train is just about to go past.
And it's just as impressive from inside the train.
We're now approaching the fastest part of the track. Let's go and take a look and see what speed we're actually doing. If I go up here and just check the driver's screen, and we're doing over 300 kilometers per hour. We're still increasing speed now. It's probably about 325, 330.
That's already faster than the TGV, and we're still picking up speed.
Very exciting, it really is. If we look out the front, we can see that we really are moving. The sensation of speed is phenomenal. Look at that. We're now approaching the top speed, 390, 400. We are at 400 kilometers an hour.
At that speed, you could go right across Europe from Paris to Moscow in just 6 hours. On October the 11th, 2003, the Germans got one up on the Japanese when a 30-kilometer track between the city of Shanghai and its airport opened its doors to the public. Using the German transrapid technology, this billion-euro project became the world's fastest passenger train, regularly topping 430 kilometers an hour.
This is a fantastic piece of kit, but countries aren't exactly queuing up to take on this technology. The problem might have something to do with the cost, somewhere in the region of 50 million euros per mile to create a maglev system.
Unlike City of Truro and the TGV, it seems that for maglev, simply being the fastest isn't going to be enough. Maglev is going to have to get an awful lot faster. And in theory, at least, that's already possible. By building vacuum tubes for maglev trains to run in, speeds in excess of 3,500 kilometers an hour would be possible, making the trip from London to Tokyo a jaw-dropping 3.5 hours.
Now that really would be massive speed.
What is a maglev train? First of all, maglev stands for magnetic levitation. It is a train used to move people and objects from one place to another at a very fast speed. These type of trains use electromagnets producing a magnetic field. How does it work? The train hovers above the ground, which means there is no friction, which is the reason why it is extremely fast. The levitation of the train is caused by the electromagnetic propulsion system. The bottom of the train is attracted upward toward the bottom of the track, while the guidance magnet is used to keep the train going along a specific track as it levitates above the track. The guidance magnet is an electromagnet which constantly reverses its poles depending on the direction of the current flow, which as a result causes the train to move and stop when needed. The magnets immediately in front of the train use forces of attraction between opposite poles to pull the train forward, while the magnets immediately behind the train use forces of repulsion between similar poles to push the train forward. And that is how a maglev train works.
Shanghai, with all the fascination of a large exotic city, pulsating lifestyle and people on the move. A city with a proud tradition, yet always open to the new. Shanghai is also setting new standards in the field of transportation, for it has something the rest of the world does not have yet: the transrapid superspeed maglev system. Contactless magnetic levitation technology. It's fast, cost-effective, and environmentally friendly. And it's also adding a new quality to the concept of mobility. The transrapid maglev connects Longyang Road Station with Pudong International Airport. In Shanghai, air travel begins and ends with a flight at 0 altitude in first-class comfort. Transrapid accelerates to 267 miles per hour in no time at all. The Transrapid is comfortable, safe, and quiet as it wings its way to Asia's most modern international airport. Flying at 0 altitude at a speed of 267 miles per hour, the Shanghai Transrapid offers the utmost in safety, comfort, and punctuality.
The Transrapid maglev system, an entirely new train system, the first to overcome the limitations of wheel and rail. Because the vehicle moves entirely without contact, it makes train travel faster, easier on the environment, and more economical. The functions of the wheel and rail on a normal railroad, including support, guidance, propulsion, and braking, are accomplished in the Transrapid through an electromagnetic levitation and propulsion system. Mechanics have been replaced by electronics. Support magnets draw the vehicle towards the guideway from below, while guidance magnets hold it laterally on track. These support and guidance magnets are mounted on both sides of the vehicle along its entire length. An electronic control system ensures that it levitates at a constant height of 10 millimeters above the guideway. While levitating, the vehicle has 15 centimeters of clearance. The maglev train is propelled and braked by a synchronous long-stator linear motor. This motor is not located in the vehicle itself, but rather in the guideway. It functions on the same principle as a traditional rotating electrical motor, whose stator has been cut open, unrolled, and stretched lengthwise along both sides of the guideway. But instead of a rotating magnetic field, a traveling magnetic field is generated in the windings, one that pulls the vehicle along the guideway without contact. The transrapid guideway can run at ground level or be elevated, which allows it to be flexibly adapted to individual operating circumstances. The guideway can be elevated where it makes ecological sense. In this case, it won't divide the landscape or developed areas. And the area beneath the guideway can continue to be used as before. The guideway can be built at ground level, for example, to minimize visual impacts or allow easier co-location with existing transportation systems. In any case, the maglev system's guideway requires less land and space than other transportation systems. The transrapid vehicle changes tracks by using bendable steel switches. These switches consist of a continuous steel beam elastically bent by an electromechanical setting drive to achieve a smooth turnout. In the bent position, the vehicle can pass over the switch at speeds up to 200 kilometers per hour. In the straight position, the vehicle can run at full operating speed. Transrapid has very favorable alignment parameters with small curve radii and a grade climbing ability of 10%. The transrapid guideway can therefore be adapted to the landscape instead of the other way around. The operation control system controls and safeguards the vehicles, switches, guideway, and stations along the maglev route. The vehicle communicates with the control system by means of directional radio data transmission. The vehicle's location is monitored by means of a location reference system integrated into the guideway. The only motor section in operation along the guideway is the one in which the vehicle is currently traveling. When the vehicle passes from one section to the next, the new motor section is automatically switched on. More power is supplied on gradients and acceleration segments along the route than on flat segments. This way, the propulsion power is distributed very economically. It's always available exactly where it's needed. Non-contact technology makes the transrapid very fast. It is designed for operating speeds of between 300 and 500 kilometers per hour. This enables trip times over medium and long distances, which have until now only been achieved by aircraft. The transrapid requires less than 2 minutes and a stretch of only 5 kilometers to accelerate from 0 to 300 kilometers per hour. The maglev system requires significantly less energy than other transportation systems. Used under similar conditions, the specific primary energy requirement of a car is 3 times higher and that of an airplane 5 times higher than the transrapid. Beyond that, the transrapid generates no rolling or motor noise. Even at 200 kilometers per hour, it's hardly audible. At this speed, the vehicle glides quietly through cities and population centers. The non-contact technology is also an important economic factor. Due to the low maintenance requirements and energy consumption, the operating costs of the maglev system are lower than those of high-speed trains. Infrastructure costs are approximately the same. The smallest transrapid train set consists of 2 sections. Depending on passenger numbers, vehicles with up to 10 sections can be operated. For high-value cargo transport, container sections with a capacity of 15 tons each can also be used. The transrapid maglev system offers a high level of comfort and safety. The non-contact levitation and propulsion technology guarantees absolutely smooth running. No jolting can be felt. Passengers don't have to wear safety belts and are free to move about the cars. The innovative technology provided by the transrapid maglev system opens up new dimensions in rail travel. Flying on the ground with the Transrapid is easy on the environment, safe, comfortable, and brings passengers directly to the city centers. Whether short or long haul, non-contact technology makes the Transrapid maglev system the best connection.
ये एक बहुत ही सुंदर मैगलेव ट्रेन या मैग्नेटिक लेविटेशन ट्रेन का मॉडल है। इसको एलजी कोरिया ने डिजाइन करा है। इसके अंदर रबराइज मैग्नेट के ट्रैक्स हैं। जैसे फ्रिज में चुंबक लगता है रबर का बना हुआ, उसी तरह से ये फ्लेक्सिबल हैं। जब सम ध्रुवों को पास लाया जाता है तो एक दूसरे को रिपेल करते हैं और असम ध्रुव एक दूसरे को आकर्षित करते हैं। ये है प्लास्टिक का ट्रैक जिसके अंदर ये मैग्नेटिक की स्ट्रिप्स जो हैं वो एकदम फिट हो जाएंगी। ये ध्यान रखिएगा कि सारी स्ट्रिप्स के ध्रुव एक ही ओर हों। तो ये तो हो गया आपका रेल का ट्रैक। उसके बाद में ये एक छोटा सा सर्किट है जिसके अंदर एक पंखा है, एक खिलौने का मोटर है, एक स्विच है और एक 3 वोल्ट की बैटरी है। स्विच को ऑन करने पर पंखा जोरों से चलता है। और ये एक चैसिस है ट्रेन की जिसमें सबसे पहले तो आप चुंबक की पट्टियां लगाएं, फिट कर दें। इसमें अलग अलग तरह के खांचे बने हैं। अब ये देखिए इस खांचे के अंदर जो स्विच है सर्किट का वो एकदम जा करके बैठ जाएगा। ये बैटरी का पैकेट बैठ गया और यहाँ पर मोटर फिट हो गया। अगर हम स्विच को ऑन करेंगे तो पंखा फर करके घूमेगा। अब ट्रेन को जैसे ही हम ट्रैक के ऊपर रखते हैं समध्रुवों की वजह से वो ऊपर को उछाल मारता है, थोड़ा सा लिफ्ट मिलती है। अगर थोड़ा सा उसको टिल्ट करेंगे तो आप देखेंगे ट्रेन जो है अपने आप ढलान से ही आगे पीछे घूमती है क्योंकि घर्षण बहुत कम है। और जैसे ही पंखा ऑन करते हैं वो आगे को हवा फेंकता है और ट्रेन पीछे को तेजी से खिसकती है। यही सिद्धांत है किसी भी मैग्नेटिक लेविटेशन ट्रेन का। इसमें न्यूटन का सिद्धांत भी एकदम साफ तौर पे समझ में आता है कि एवरी एक्शन हैज ए इक्वल एंड ऑपोजिट रिएक्शन। हर एक क्रिया की एक प्रतिक्रिया होती है। पंखा आगे हवा फेंकता है और उससे ट्रेन पीछे को जाती है। और क्योंकि घर्षण ट्रेन और ट्रैक के बीच में बहुत कम है इसलिए बहुत तेजी से जाती है। आजकल दुनिया के बहुत से हिस्सों के अंदर मैग्नेटिक लेविटेशन ट्रेन्स आ रही हैं जो बहुत तेज गति से चलती हैं। और इसकी एक छोटी सी झलक बच्चे इस छोटे से खिलौने में देख सकते हैं।